are 7 radical expressions. Okay, so we've already talked a little bit about radicals because we talked about rational exponents. And so we had a to the 1 over n is equal to the nth root of a. So we're already talking about radical expressions. Now, let's just go back into this as a refresher. In a radical expression, whatever is underneath this symbol is called the radicand. That symbol is called the radical. And this, in this case, a letter or number, is called the index. Now, I know I've been using these terms as we were going through this, talking about rational expressions, but I just want to make sure that we're all in agreement and understanding of what those different things are. So, the radicand, the index, and then the radical. And many times mathematicians and scientists will refer to those as radicals instead of the square root symbol or the cube root symbol. It's just a radical. So we've got that to deal with. Well, let's do some figuring out. Now remember that I said that when we have a radical and it has an even index, that we generally accept that as being the positive root. So if we have the nth root of a, where n is even, then we look at this as saying that we're going to use the positive root of that. If we want the negative root, we say negative nth root of a. And then we'll give the negative root. I don't know why I keep putting a 2 for square root. If we have the square root of 9, then that would be 3. But if we have the negative square root of 9, that would be negative 3. And that's why we actually, when we're dealing with the quadratic formula, you say plus or minus the radical of, because that forces us to use the positive root and to use the negative root. And when we're solving, when we have something squared, so we take the square root of both sides, we say plus or minus because that's telling us we want the positive and the negative root involved. Let me grab my paper that decided to jump to the floor. Sometimes they have the desire to end their life quickly. Papers are like that. So let's look at a few radicals and see what the result is. Let's go for a fourth root. The fourth root of 81. Well, the fourth root of 81, it's an even radical, even index, so we're going to go for the positive root, and that's 3. If I say negative fourth root of 81, it's telling us we want the negative root, so that's negative 3. If I would ask for the fourth root of negative 81, be careful. Although a negative inside a square root puts you to a complex number, an imaginary number, if we, such as the square root of negative 25 would be 5i. Such is not the case for the fourth root of that. This is not 3i. Because 3i times 3i would be 9i squared, or negative 9. And then negative 9 times negative 9 would be positive 81, not negative 81. So be careful of that. The only time you can look at that negative is when you've got the square root. So just be careful of that. Okay, so what if we looked at radicals and rational exponents. We're going to kind of refresh that. We're going to bounce back and forth. So if we write something as an expression with a rational exponent, let's convert that to an expression in terms of a radical, and then we'll do the opposite. We'll start with an expression in terms of a radical, and we'll turn that into an expression in terms of a rational exponent, just to make sure that we've practiced that a little bit. So if I have 5 to the 3/7, that's a number raised to a rational exponent. We can then write that in terms of a radical as, remember, the numerator is the power, the denominator is the index of the radical, the 7th root of 5 cubed. What if I have the cubed root of 2 to the 5th? And we want to convert that to an expression with a rational exponent. Well, again, the numerator is the power, the denominator is the index, so that would be 2 to the 5/3. And remember, that is equal to the cubed root of 2 to the 5th. These two are equivalent. So just keep that in mind as we go through this. Well, let's evaluate some of these. We're going to start with some cancellation because this is going to prepare us for simplification. If I have the 6th root of w to the 6th, remember what that's really saying. If we write this in terms of a rational exponent, that's the denominator and that's the numerator, so you have w to the 6/6. You simplify 6 divided by 6, that's 1, so you just have w. So relatively straightforward in how we work with that. Let's get into rules for these radicals. We had the rules for exponents. Well, what are the rules for radicals? How do they combine? And remember that a radical is just a rational exponent. So they should follow the same rules. So if we have the product rule, what if we have, so let's put some of these rules together. Now, these rules follow the same idea as they did for the exponents, but they may seem just a little bit different. The product rule, what we call the product rule for radicals, will look a little bit more like one of our power rules. And same thing with the quotient rule for radicals. So if we look at the product rule, that just says that the nth root of A times the nth root of B is equal to the nth root of A times B. So basically we can distribute it through or pull it out, depending. The quotient rule, the nth root of A over the nth root of B is equal to the nth root of A over B. And the power rule go on, erase that. If we have the nth root of the nth root of A, that is equal to m times n of A. So let's put some of these to use. So just to refresh again, if we have the same index, if we have the same index, then, or the product, then we can multiply and hold that index. If we have the same index for a quotient, then we can put it all together under that same index. And if we raise an index to another index, raise a power to a power, raise an index to an index, then we multiply those indices. So let's play with these a little bit. Okay, so let's go with the square root of 24 times the square root of 6. Same index, product, so we can turn that into the square root of 24 times 6. 24 times 6 is 144. And the square root of 144 is 12. Notice how nice that made that. What's the square root of 24? A little under 5. What's the square root of 6? Somewhere between 2 and 3. So a little under 5 multiplied by somewhere between 2 and 3. Oh, well, wait a second. 24 times 6, 144. The square root of 144, 12. So this is where you get an advantage by being able to use these rules. Let's try another one using a different one. What if we want the cubed root of x over x cubed? Well, we can use the quotient rule and say that's the cubed root of x over the cubed root of x cubed. Well, if we have the same index and the same power, they cancel each other out. So that leaves us with the cubed root of x over x. So that's nice. That allowed us to get a radical out of the denominator, because remember, we don't like radicals in the denominator. So if we can rationalize the denominator to get that radical out of there, that's a good thing. Let's try something slightly different. In fact, I'm going to leave that one up there as I do it. What about the cubed root of x cubed over x? Well, that works a little bit differently, doesn't it? If I break this apart, I get the cubed root of x cubed over the cubed root of x. Well, that's going to cancel out, so that gives me x over the cubed root of x, but I just told you we don't like to have a radical in the denominator. So what are we going to do with that? We want to rationalize this denominator. Now be careful, because this is where I see people make mistakes, is they know, oh, if you want to rationalize the denominator, just multiply it by itself and it gets rid of it. That only works if you're dealing with squared. Yeah, if you have 1 over the square root of a, then you can multiply that by the square root of a over the square root of a, and you end up with the square root of a over the square root of a squared, or I can say the square root of a squared to show it as written. And when I go square root squared, those cancel out, and we get the square root of a over a. That works for square root. When that index gets above 2, you have to account for that. And it's not that difficult to account for it. It just means we need to multiply by something that's going to raise our power to the same as the index. So that means with this, x times what is going to get us up to x cubed? X times x squared. So we want to take the cubed root of x squared. Cubed root of x squared. So now we end up with x times x squared is x cubed. And so we have x times the cubed root of x squared over the cubed root of x cubed. That cancels out, gives us x cubed, x times the cubed root of x squared over x. The x's can cancel out, and we end up with the cubed root of x squared. Now let me bring something up that you might have caught as I did this. We have to be very careful when we're dealing with indices, or the index here, right? Because notice how when I wrote it like this, I accidentally stated that as x cubed. You really have to be careful to make sure that that is really in and a part of your radical, that it shows that that is the index. Because there's not much difference. Like you look at this bottom one here with the spacing I have, if I put a y there, doesn't that look like y cubed times the square root of x cubed? So we have to be very careful about where we put our indices. Make sure you get them close to them. I got a little sloppy there, and it almost caused me to make an error. So be very careful about that. One thing that I like to do as I'm going through different things is I like to point out where common errors occur. There are a number of things that we do in mathematics that can create an error for us. So if we can be careful and follow some basic steps, we can kind of avoid those issues. It's kind of like when we were dealing with adding or subtracting polynomials. When you subtract polynomials, if you're not careful, you can get yourself in a position where you don't distribute through the negative sign. When we were factoring polynomials, if you end up with the greatest common factor, like if we were doing factoring by grouping, and you came out with a greatest common factor of 1, you've got to pull out that 1, otherwise you end up making a mistake. Same here, when you're dealing with those indices, make sure that your index is really attached to that radical sign. Otherwise, it's very easy for it to be misunderstood. Also, something to be careful of is subscripts. Subscripts you need to be careful of to make sure that they actually show as subscripts as opposed to being the same level as everything else. So watch out for those things as you're doing it. I'm just going to swap papers here because we're going to get into simplifying radicals and doing some major simplification here. So let's look at some examples. Let's see. First one I do, just -8 times the cubed root of 125. Okay, so Negative 8 times the cube root of 125. Well, what we're going to look at first, we're going to take, remember order of operations. Order of operations does not change just because we're working on other things. Order of operations says parentheses or grouping first. So anything inside this radical would be worked on first because that's grouping. It then says exponents. Remember that the index of a radical is an exponent. It's the denominator of an exponent. So we're going to perform this radical first before we do anything else here. So it's equal to negative 8 times, well, the cube root of 125 is 5. Now we can do negative 8 times 5 is negative 40. So that one wasn't too bad. Well, let's look at some, shall we say, a slightly more complicated simplification. I'm going to get this out of here, and I'm going to make this other one come in, because this shows a good example of us having to look a little deeper into what's happening. The cubed root of 128, I'm going to need more of that, okay? A to the 6th, B to the 8th, C to the 10th. Now remember, when we were dealing with rationalizing that denominator, the goal was to get the power inside the radical to be the same as the index of the radical. And we did that, we could get rid of the radical, we could cancel it out. Well, the same thing happens here. And the nice thing is we can deal with this as simple division with a remainder. So looking at this, well, 128, can I do anything with 128? I don't recognize 128 as being a perfect cube, but I do know that 64, which is half of 128, is a perfect cube. It's 4 cubed. So what I'm going to do is I'm going to take this cubed root and I'm going to make it 2 times 64. A to the 6, B to the 8, C to the 10. Now I'm going to rewrite that 64 as 4 to the 3. 2 times 4 cubed. Now what I'm going to do with these is I see A to the 6th, well, 3 goes into 6 2 times. So I can write that as A squared to the 3. Why do I put the 3 on the outside? Because I want it to be able to cancel with that. Well, what about this B? Well, 3 goes into B, goes into 8 2 times. So I can write that as B squared cubed with a remainder of 2, B squared. Can't raise it to a power because I couldn't get it up to 3. And then C to the 10th, 10 divided by 3 is 3, so C cubed with a remainder of 1, C. So now that I've done that, anything that has a cube for the power, I can cancel and pull out. So I have 4 cubed, so that's 4. I have A squared cubed, A squared, B squared cubed, B squared, C cubed cubed, C cubed, and then anything else remains in my radical. Notice how I tied that 3 really closely to that radical, leaving me with, well, I already took care of that, and that. So that leaves me with 2 B squared C. So what did I do? I used the power rule to create a base raised to the correct power to cancel this out. And I used all that I could, I got the highest amount I could, anything left over had to stick in the radical. We couldn't get rid of it. So we were able to pull out the 4 because we had 4 cubed, which canceled out with the cubed root. We had a squared cubed, which canceled out with the cubed root, so that brought out the a squared, b squared, cubed, c cubed, cubed, and then it left us with our cubed root of 2, b squared, c. Now, if you remember with long division, when you first learned long division and they talked about fraction, you started with long division and first thing you did was you just divided things that divided evenly. And then you went into things that divided evenly with a remainder. And then you went from things that divided evenly with a remainder to things that divided evenly with a remainder, where that remainder turned into a fraction because it was left to be divided by whatever the divisor was. Well, it's the same idea here, that we take it to where we can cancel, and then the remainder is what stays inside that radical. Okay, just need to grab some here. Okay. Let's get into a little more exciting thing with simplifying radicals. What if we have a radical inside a radical? Well, that could be interesting, right? So what if we have, let's get rid of this red pen. I'm kind of sick of that one. Let's go back to go to the black. So what if I have the 6th root of the cubed root of 4 squared? The 6th root of the cubed root of 4 squared. Well, remember our power rule said that if we have a radical inside a radical, we can multiply the indices. So that's going to give us 6 times 3 is 18, so the 18th root of 4 squared. Well, I said that you could cancel if you had the same power, right? Because what's really happening? You're dealing with the power is the numerator and the index is the denominator of a rational exponent. So knowing that, this is really 4 to the 2/18. Well, 2/18, we have a common factor, 2. So I can make this 4 to the 2/18, and I can take that and I'll go, well, wait a second, well, that's the same as 4 to the 1/9. Or I can come right from here and say, well, there's a common factor in this, so I can cancel it out, giving me the 9th root of 4. So that's not too bad. So it's kind of handy. So we did this and we came out with a common, and we came out with our final index by multiplying the indices, and then we're able to cancel against that to simplify it down. So we started with the 6th root of the cubed root of 4 squared and ended up with the 9th root of 4. So kind of handy how that works. Now let's look at multiplying radical expressions. Okay, so what if we have, let's say the square root, I'm just trying to see, I have something written here and I want to make sure I put it down right. Let's say we have the square root of 11 plus the square root of 17 times the square root of 11 minus the square root of 17. Now I'm sure I chose these because those being prime numbers, you're not going to find the square root of them, at least not with anything that's going to be nice. They're going to be irrational numbers. But let's see what happens when we do that. And if some of you may remember and recognize, if we have the sum and the difference, that we usually call those the conjugates. And something happens when you have conjugates. So how do we deal with this? We have the product of a sum and a difference. Well, we can deal with it by using basic FOIL. FOIL does not just work for polynomials and variables. FOIL works for any time you have the sum of two things multiplied by the sum of two things. Remember that subtraction is really just addition of dealing with a negative number. So we can do first, so the square root of 11 times the square root of 11 is the square root of 11 squared. Outer plus the square root of 11 well, actually, I'm going to write this a little differently here because we don't want to. Well, actually, I can do that. So I can do that times the negative square root of 17. I just didn't want to accidentally put the negative inside the radical because that would be bad. So times the negative square root of 17, and then the inner plus the square root of 17 times the square root of 11. And then last, the square root of 17 times the negative square root of 17. Okay, so what does that do to us? Well, negative square root of 17 times the negative square root of 17 is going to give us the negative square root of 17 squared, right? Negative times positive, going to get a negative result. So I'm going to put the square root of 11 squared here, just because I can, and we already had it there. I'm going to put minus the square root of 17 squared there. And then I've got square root of 11 times the square root of times the negative of square root of 17. So I'm going to say negative square root of 11 square root of 17 plus the square root of 11 square root of 17 minus square root of 11 square root of 17 plus square root of 11 square root of 17. So I could go through the effort of multiplying square root of 11 times 17 or 11 times 17, but I'm not going to. I just noticed that that's minus, that's plus, so those cancel out. Square root of 11 squared, the square root and the square cancel, so we have 11 minus square root of 17 squared, the square root and the square cancel, minus 17 gives us negative 6. So it's the same thing, we're just doing FOIL, just be careful where those negative signs and don't forget about the negative signs. Now, some of you may have recognized this immediately as the product of a sum and a difference, which if you have the product of a sum and a difference, then it's the square of the first term minus the square of the second term. The square of the first term minus the square of the second term. And in this case, because we're dealing with square roots, they cancel out, disappear, and you just end up with the value minus the other value, and we're able to do the calculation. So that's multiplying radical expressions. Okay, what about rationalizing the denominator? And we actually already dealt with that. So I think I'm going to kind of skip over that right now because we did rationalize the denominator. Just remember that when you rationalize a denominator, you're trying to make the power of the radicand match the index associated with the radicand. So let's take this to something a little more exciting and get into simplifying radical expressions with fractions. Or rational radicals, if you want to go that far. So let's go for the cubed root of a to the fifth b over the cubed root of a squared b cubed. Okay, so if we have this, what can we do? We have different radicands, but we have the same index. So this is actually the quotient rule. So we can take this as the cubed root of a to the fifth b over a squared b cubed. Well, now that we have that, we have a rational expression with same bases and different powers, so we've got this quotient. So we can do the canceling. 5 minus 2 is 3, 1 minus 3 is negative 2. So we can turn this into the cubed root of a cubed over b squared. Now, if that threw you off for a moment when I said b squared, remember, b minus 3 is, 1 minus 3 is negative 2, which flips it to make it positive 2, right? You take the reciprocal of it. So what we can do is I can go from here and I can go into it and say, okay, that's the cubed root of a cubed b to the negative 2. But once I do that, I'm going to want to make that positive anyway. How do I do that? I put it in the denominator is equal to the cubed root of a cubed over b squared. So I just did that right there. But there's one more step that we may want to do with this. We're really looking at a radical in the denominator. And that we don't like. So I'm going to take it another step here and rationalize that, or take it 2 steps. I'll break it back up into the original pieces. So I'm going to make this the cubed root of a cubed over the cubed root of b squared. First of all, if I have the cubed root of a cubed, we know we can cancel that out. So we have a over the cubed root of b squared. So if I want this to cancel that, I've got b squared, I just need to multiply by the cubed root of b. I just need another b in there. So I can say a cubed root of b over the cubed root of b squared times b, which is b cubed. So that's a cubed root of b over the cubed root of b cubed, which the cubed root and cubed cancel out, giving me a cubed root of b over b. So, took a number of steps and then we rationalized the denominator, but again, it was little steps. Just take them one at a time. Don't let it overwhelm you. So there's one more thing I want to bring up in this, and that's what if we want to try to rationalize a denominator and it has the sum or a difference that includes a radical but not both include the radical. 2 over 3 plus the square root of 5. Well, we know if we have the square root of 5, if we just had this, we would just multiply the top and bottom by the square root of 5 and we'd be done. But we don't, we have this 3 here. So this is where we bring in the conjugate. The conjugate works that, remember we showed the example with the square root of 11 plus the square root of 17, multiplied by the square root of 11 minus the square root of 17, and the product of the sum of the difference, it eliminated the radicals everywhere. Well, we can use the same process here, and it'll eliminate the radical, and this never had the radical, so it's not gonna suddenly become a radical, it's just gonna increase that a little bit. So what we can do is multiply this by 3 minus radical 5, 3 minus radical 5, and then we can distribute through on the top. That's going to give us 6 minus 2 radical 5. And on the bottom, we're going to be taking FOIL, but in this case, we know what's going to happen, the product of the sum of the difference. We're going to square the first one. 3 squared is 9. And then we're going to subtract the square of the second one. Square root of 5 squared is 5. So that takes us to 6 minus 2 radical 5 over 9 minus 5 is 4. And just to finish it off, we've got 6, negative 2, and 4. We can factor out a 2 throughout there, which gives us 3 minus radical 5 over 2. So we can rationalize a binomial denominator whether it has a radical in it, or 2 radicals, or no radical.